So you should be seeing my my screen now. We're still going to run on Setonix, just not as nicely in a Jupyter notebook, but that's something maybe we can figure out for the Q&A. I'm an engineer. I guess probably most people in the room are. I don't know who here is a physicist. Maybe you can, let's try to do this interactive. You can lift your hands. Oh, actually, I stopped sharing here. Actually, I don't see your hands, but anyway, you can let me know in the chat. I'll probably see your messages. If you are a physicist and you already know everything about quantum computing, that's okay. And if you don't know anything, that's also okay. So lift your hands if you feel like you're an expert in quantum computing. All right, lift your hands if you feel like you're intermediate in quantum computing. Nobody. Okay, one person.
But we might not need to.
All right. And now Noah, you can lower your hand, and everybody lift your hands if you feel like you're starting with quantum computing. Okay, great.
I'm raising my hand. I don't have any hand raised, I can see.
Perfect. All right. All right. So then I will not go through the physics of what happens here. Not a lot, just a little bit. And this is okay. So as I told you, I'm an engineer. I didn't need to learn about everything in the physics. I do know how these computers work, but you don't need to. You don't need to learn how they work at the physical level in order to use them. There are some things that you do need to know, and you will need to program them into your algorithms, etc. How you're going to solve your problems. I swear it's easier than what we did in the last 40 minutes. I believe quantum computing is easier than containers. All right. Something in case you're interested, there's a lot of resources available online. I will share some at the end. So if you get lost, if there's something you didn't understand, you want to learn more, I will share some resources. That is definitely how I started. I listened to a talk, I understood about half of it, and then I did a deep dive and just couldn't leave the field because it was so exciting. It's an exciting moment to work in a field that is changing and is being built as we speak. So the first question is, why do we even need quantum computing? Why would we use it? Some interesting use cases are chemistry, optimization, and machine learning. In chemistry in particular, you can think of, well, quantum computers are these devices that use the properties of quantum mechanics. They use properties called superposition and interference and entanglement. So they work differently to the classical computers that we have, which use transistors, right? So you all probably know something about computers, right? You are in an HPC setting, and classical computers work with transistors. They are more like switches, while quantum computers work with different kinds of underlying technologies that leverage those specific properties that only happen at a very small scale. So it's not something that we will see in our daily lives. It's why it's hard a little bit to explain exactly how they work, because it's not something we can relate to so much. It's not something we live in our daily lives. But the key point here is that the quantum computers are not just a larger classical computer. Their physics of how they work is intrinsically different. And this is why it's interesting to use these quantum computers for problems such as chemistry, because chemical problems behave in a similar way to quantum computers. So if we can make quantum computers behave in the same way as molecules, for example, then you might be able to simulate interesting materials or discover properties from materials without needing the material itself. So you wouldn't need so many tests, lab tests, etc., or you would be able to understand those materials to a higher level of precision. If you can use a quantum computer to make it have a behavior that represents what is happening in a chemical system. That's because we don't need to program, the equations that govern those rules of quantum mechanics. We can just let them run, right? If the quantum computers already have that quantum mechanics intrinsically in them, then you don't need to program, the mathematical description of it. For optimization and machine learning, it's a little bit different. It's now that we know that we can build these quantum computers, can we use the math that describes those quantum computers? Can we interpret, or can we encode different kind of problems and interpret the results? So can we use those quantum computers for more than literally simulating those chemical processes, for example? And the answer is yes. And a lot of people are interested in problems related to optimization, for example. So if we encode a specific optimization problem, I'm going to say, for example, a logistics problem or a finance problem, you encode it into the behavior of a quantum system and then make it evolve, or evolve under certain circumstances. You can modify it in certain ways to try to predict the output of that optimization problem. So you can do minimization through a quantum computer. And most of the time, like, we're in exploration. So for now, most of the time, there's no clear advantage. But if those quantum computers get very big and very powerful, then there might be an advantage in using quantum computers for problems that involve a lot of, for example, vector matrix multiplication, because this is the same math that we can use to describe quantum computers. Machine learning, similar thing. What if we could use quantum computers to enhance what the classical ones do? And so in the end, quantum computers don't come to replace classical one. And if, there are two things that I would like for you to remember after this. Okay, 3. First, quantum computers are more like a GPU to a CPU. They're a complement. They can help to resolve powerful problems, but they will not solve everything. Sometimes they will make things slower. And they're more of a complement to what we have in classical computing. The other things I want you to remember is that you can go to PennyLane.ai. I'll show you the link at the end, and there you can find all of the resources. And there's an event that I want to mention at the end. But for now, just to get the context, quantum computers work with a different physics. They're used for specific problems, not for all problems. And they work together with classical computers. I'm going to mention some features today, but I'm going to go a little bit fast over this section also, so that we can get some more time for some hands-on demos. And I'm going to mention a little bit about Xanadu, the company that I work for, and PennyLane. So Xanadu is a full-stack quantum computing company, and our mission guides everything that we do. It's a twofold mission. On one hand, we want to build quantum computers that are useful. This means making quantum computers that are performant, that are large, that can solve real problems. So this is a hardware effort. And on the other hand, we want people to be able to use it. We know that even if we have the best tool, we need people to use it in order for it to be useful, right? If nobody knows how to use it, then it's only half the job done. So this mission guides our motivation to create and maintain libraries such as PennyLane. PennyLane is our main library, and I'll tell you more about it later. In terms of the hardware, our strategy, or our hardware, focuses on using photonics. So we use light, laser light, similar to the ones that takes internet to your work, to your home, etc. So if you have internet coming by fiber, that fiber optics is similar to the one you see in the picture. So on the left and right, you see some fiber optics. It's a probably a very similar fiber to the one that takes internet to your home or to your work. In the middle, however, you see a chip. This is because we do integrated nanophotonics. So we pass that light through waveguides in the chip. So you can imagine as like narrow corridors in the chip, and that modifies the way that light behaves. So it's not enough to have any laser. It's not just a powerful laser. You need to modify the state, or basically you need to modify the way you can describe that light. So you modify the state of that light, and then that turns it into something that has those quantum properties that we can exploit. So we can use stuff called gates, and then we can modify the state or the behavior of that light, and we can perform computations with it. Now the chips on their own do nothing, right? A quantum computer is a system that integrates a lot of things. So you have the lasers, you have the cable or the fiber, you have the chips, you have software, you have controllers, you have a lot of things that have to come together. And we do everything from the design, from thinking about how these quantum computers can be made and work and be more performant. We design those quantum chips. We send them to foundries to fabricate, but we test them in-house. And we package them into systems that are complete. We also create different software. So PennyLane is the main one, but we have a bunch of software products that we use along our stack. And we do research on different applications. So we have two main research groups, one on quantum machine learning and one on algorithms and chemistry. So battery simulation is our most applied and our main area of applied research. How to simulate the batteries of the future. Today, they're very complicated systems, right? They use materials that are very complicated to understand to a high level of detail. And the goal is to be able to simulate these with quantum computers. So I think somebody had a question. I heard somebody. No? If you do have a question, this is a good moment. All right. We have different kinds of hardware that we have developed over the years. In 2019, we put the first photonic quantum computer on the cloud. It's still online, available for people to use. It's mostly for research and education in photonics, in quantum photonics. We had one quantum computer that made the headlines everywhere. This was not a chip. This did not use any chip. This actually took an entire optical table, which is maybe 2 meters long by 1 meter wide, maybe a little bit more. And this made the headlines because it solved a problem that was considered practically, like realistically unsolvable on a classical computer. It's not a particularly useful problem, so it was just chosen because it was a hard problem for classical computers. And so for one sample of this specific problem, it took 36 microseconds in this computer, and it would have taken 9,000 years in a classical one. So it just shows the magnitude of the difference, you know, between what classical and quantum can do. Of course, this experiment was designed specifically for that, so we chose a problem that was specifically hard for classical computers, and it doesn't have, as far as we know, any practical application. Now, that was our previous generation, and now we are working on our first fault-tolerant module. So what this means is current quantum computers, you will notice that they don't always give you the right answer. Sometimes it's like having a calculator that if you ask it to add 1 + 1, it sometimes says 3 and sometimes says 1. So not great if you want, you want to know what is 1 + 1. So aside from the fact that quantum computers are not great at adding, they also have, errors. They have a lot of noise. They have a lot of noise that is intrinsic to the way they're built. So we're working on building the first fault-tolerant quantum computer. So the first fault-tolerant modules which have error correction protocols. So these are not the same as in classical, error correction. There are specific protocols that are researched for making these devices. And the goal in the future is to have something like a quantum data center or a hybrid data center, where you can run your different problems with quantum, different quantum computers. Don't necessarily have to buy them and have them at home or at the office. You can probably access them on the cloud. And in particular, our architecture is based on something called measurement-based quantum computing. So for those of you who are intermediate in quantum computing, maybe you've heard of this, or advanced. This basically means you are adding some settings, which are some gates. So this, what you see at the bottom, X, Z, CZ, etc. You set that into the quantum computer that performs a specific measurement on your qubits. Your qubits are your main unit of computation. So they are kind of like what would be the equivalent of the bits, but they don't work exactly the same, but they're the unit of information. In our case, they're a specific state of light that allows us to, that has the properties to be considered a qubit, and that allows us to perform, the computations. So we send some settings, we get some measurements in return, and then we can analyze that information. Did somebody have a question? I saw somebody unmuted themselves earlier. No, maybe it was an accident. Or yes, Amir?
No question for me.
No? Okay. All right. Some benefits are the fact that this is scalable. If we want to build useful quantum computers, we will need to build very big quantum computers. And so we will need to make them scalable. And because they use technologies that are already standard, like fiber optics or silicon nitride chips, that's already something that the world can produce. And because also we work with fiber, we have the flexibility of changing them around and trying different error correction codes. Of course, we don't work alone. We partner with different organizations who are part of the quantum ecosystem on different areas, hardware, software, and applications. I'm very glad to be here talking to you about quantum computing, because you are the main candidates. And you have hard problems to solve, and you know how to use performant resources. So I hope this can help you as an additional tool in your toolkit that will allow you to solve those hard problems that you're now solving on Setonix. So now this is an additional tool that you have available for you. Today we're going to focus on PennyLane, which is the main library. So you've heard about PennyLane with the installation of everything. You've heard about PennyLane. This is an open source library. It's Python based, so easy to code. Requires just basic Python, nothing too advanced. And it's a community project. So while Xanadu is the main maintainer, it is really an open source project, a patch 2.0. So you can build your own projects on top of PennyLane. And there are companies, researchers, students, everybody, a lot of people using PennyLane. We have built it as a quality tool for solving hard problems. And I hope you enjoyed, and if you do have any feedback, that's how we get better. We get better from, from your thoughts on using it.